Welcome to another lesson of sectoral structures theory. We will begin talking about a specific part of this theory over the next few videos, which focuses on the intersection between sectoral structures theory and graph theory. In this context, we're going to look at sectoral structures as graphs. And we've seen when we looked at the mean function in how which shows how the sizes of sets of various degrees grow as n increases. We've seen that there's a very direct correlation between that and between the enumeration of caterpillar plots. Um, and here, this also shows us how we can think of sectoral structures as graphs. However, to keep it relevant, we're gonna note some distinctions. We're not gonna use the language of graph theory, but rather the language of sectoral structures theory. Uh, Today we will begin with the basics. So we have here a sectoral structure. And just a quick reminder in that a sectoral structure is any sectoral sequence whose total curve length is 2 pi. So basically, the length of the curve between one end and the other is 2 pi. And if you remember, we called each of the two ends a delta joint. And we also have here the beta joints, as a reminder, are the connections between two alternating sectors, while the alpha joints are the connections between two continuous sectors. We've seen previously that n, or the degree of the sectoral structure, is also equal to the total number of alpha joints and beta joints plus 1. So here n is equal to 5, and we've got 2 beta joints, 2 alpha joints, that's 4 plus 1 gives us 5. Again, we also saw that the order of a sectoral structure is equal to the number of distinct parts that it has. In this case, for example, it has 3 parts. So the order, or lambda, is equal to 3. And another important connection is that the order is equal to the number of beta joints plus 1. So now we will review or define some concepts that will help us study sectoral structures as graphs or as sectoral graphs. So V will be the vertices, and here we see V. V is another way of identifying parts. So each vertex is really one part or equal to one part. The difference is that V is simply one point, while the part is composed of all the sectors of that structure. And again, this helps us visualize these as caterpillar graphs. So V is the same as or equal to lambda, which is equal to beta plus 1. Now J will be the total number of joints. So this will include the alpha joints, the beta joints, and the delta joints. And now a quick reminder, most sectoral structures are what is called open sectoral structures. The one exception, or the set of exceptions, are the theta structures, which are basically a circle divided into equal parts. It looks like a pizza, because there we have the delta joints joining and forming an alpha joint. So in a way, here we would have delta plus delta giving us an alpha joint. But overall, J is equal to, for any sectoral structure, we will define it as the total number of alpha joints plus the total number of beta joints plus the total number of delta joints. And this will also be equal to n plus 1. If you see here, we saw that n was equal to alpha plus beta plus 1. If we replace if we replace the 1 by delta, then the delta joints for an open sectoral structure are always 2. So this is why this equals to n plus 1. Next, we will define E, or the edges. We saw earlier a similar concept, but not quite. So we talked about the walk of a sectoral structure, and that is the distance, the distance between the two delta joints, not the diagonal. The diagonal is the direct linear distance, the line connecting them. But we said that the walk would be basically going over all the edges, the minimum number of edges to connect the two delta joints. So in this case, we see that the walk looks like this, something like that. And it connects the two delta joints. Now the diagonal was the direct linear distance. We're not going to be talking much about it here because this is more geometric, not graph theory. Now the edges, though, are slightly different. It includes all the elements of the walk plus the other edges as well that are not part of the walk. So here we've got two more edges to include. So the walk for this sectoral structure in this example was 1, 2, 3, 4, 5, 6 units, because each unit is 1 in length. However, E in this case is equal to 1, 2, 3, 4, 5, 6, 7, 8. Now, let's start by figuring out how to calculate E without having to draw the sectoral structure for any sectoral structure. One thing we can notice is that the walk, W, has to be included as part of E. So the walk must be less than or equal to E. And it must be included in the sum as well. And we know that W is equal to 2 times lambda, which is also 2 times V. So we will say that the total number of edges is equal to 2V plus something else is missing. What is missing? So the walk is entirely determined by the beta joints. Basically ignores the alpha joints, walks over them, or ignores them and walks through the beta joints only. So really the walk is delta to delta passing through all the beta joints. So what's missing from this are the alpha joints. So if we say 2V plus the number of alpha joints, that will give us E, or the total number of edges. Now let's write this another way. We know that V is equal to beta plus 1. We will say that instead of V, we will replace it by beta plus 1. So this gives us 2 beta plus 2 plus the alpha joints. Now we're going to reorder these variables. We're going to split the 2 beta into beta plus beta, and we will say beta plus alpha, and then we will also split this 2 into 1 plus 1. So this will be 1 plus 1, this will be beta plus beta. And here we will say beta plus 1 is left. So beta plus alpha plus 1. And the reason we did this is because this equals to the degree n. So we will say n. And we are left with beta plus 1, which is lambda. So E is equal to n plus lambda. So this is the first time we have something connecting the order and the degree of a sectoral structure. Now, if several algebraic relationships arise, and feel free to check those later, we can say that the edges minus the vertices of a sectoral structure equals to its degree. We will also notice that the edges minus the joints of a sectoral structure equal to its order minus 1. The one, sometimes you will notice one issue sometimes arises with theta structures. However, most of the time, actually, these same rules also apply to sectoral structures. But I always prefer to talk about open sectoral structures because the closed ones or the theta structures act a little bit differently. Later on, we will see other examples of closed sequences, but they won't be structures. But however, now we are really mostly focusing on the open sectoral structures, but incidentally, most of these rules also apply to the theta structures. And then we have another important connection between these three variables. We'll say V plus J minus E is always equal to 1. And this applies to both open and closed sectoral structures. So vertices plus joints minus edges always equals to 1. And we've seen similar relationships in graph theory and in topology. However, now we are focusing them in the language of sectoral structures theory. We said that the walk is equal to 2 times lambda, or 2 times v as well, which is equal to 2 beta plus 2. We've seen this just now. So what happens when we subtract the walk out of the total number of edges? So E minus W will give us, we can use this rule here. We know that E is 2 beta plus 2 plus alpha. If we want to subtract the W from it, the W will be equal to 2 lambda, which is equal to 2 times beta plus 1, which equals to 2 beta plus 2. So we are left with alpha. So E minus W is equal to alpha. And by common sense, we also can think about it that the walk spares all the alpha joints. So this is one of the important rules, E minus W equals alpha. We will also see that this also equals to, if we do some algebra, this also equals to n minus lambda. So here, why this is relevant is because we have now another relationship connecting the order and the degree. Instead of adding them, we are subtracting them. So the sum of the order and the degree of a sectoral structure is equal to E, while the difference between the order, between the degree and the order is equal to alpha. And please feel free to do this algebraically using the equations we have here to arrive at this. What else do we have here? We know that we can rearrange this to say that the walk is equal to edges minus alpha again. Now, what if we want to look at J is equal to, we know the number of joints is equal to alpha plus beta plus delta. We know that delta is an open sectoral structure is equal to 2. So we can say that J is equal to alpha plus beta plus 2. However, we know that the walk is equal to 2 beta plus 2. So we can write this as the walk minus a single beta. So we know that the total number of joints can also be written in terms of the walk. So it will be equal to alpha plus the walk minus beta. So another way to look at it, we can rearrange this into the following rule. J plus beta is equal to W plus alpha. So another nice way to correlate these. Let's look at another example. Let's look at the edges plus alpha. We know that E is equal to N plus lambda, and we know that alpha is equal to N minus lambda. If we add these two together, the lambdas go away, and we are left with E plus alpha is equal to 2n. I think this is a really nice relationship. So the edges plus alpha is equal to 2n. So we see the connection here between the alpha and the edges. So alpha, E minus alpha is equal to the walk, while E plus alpha is equal to 2n. So this will be a nice introduction into sectoral graph theory. And over the next several videos, we will do a deeper dive into these.